All right, so hello everyone. Welcome to Recitation 12 on Mechanics and Materials 1. Again, we have 4 exercises, but we mainly talk about the first 2, and I think once you learn these, then every problem similar to these would be straightforward. So this is the first one, and in a way is very similar to the problem we just solved together in the previous one, in the previous recitation, but here you want to calculate the deflection. In the one that we just did, we calculate the moment, we calculate, let's say, the diameter of the shaft, but now we have a kind of similar setup, but we want to calculate the deflection, V, as a function of x. So how do we do that? In order to calculate deflection, we start from, let's say, our magic formula for this, and that would be m moment equals EI V double prime. Okay? Now, V double prime is the second derivative of deflection V with respect to the x coordinate x, and m is a function of x. And obviously, if you can express m as a function of x, then you can immediately compute your v. So your differential equation is basically v double prime equals 1 over ei times m. And here we are lucky that, E and I, they don't change. So they are constant. We can just treat them nicely. All right, so what we need then is very similar to the previous problem, is moment m as a function of x. How do we do that? We need to calculate the moment in these 3 sections. But in order to do that, we need to also know what are the reactions at these supports. So let's say FA and FB. Again, these are 2 unknowns. These are just external unknowns. So we can simply draw our free body diagram, write our equilibrium equation, and calculate those. So this would be FA, that's FB. Again, from our equilibrium, let's say this is our free body diagram. Our first equilibrium equation is sum of the forces in y direction is 0. Assuming upward is positive, you would say then FA plus FB minus 200 minus 300 is 0. That's your first equation. The second equation would be equilibrium of moments with respect to, let's say, point A is 0, assuming, again, counterclockwise is positive. So now you have, we write it with respect to point A. So this would give us clockwise, that's minus. This one gives us counterclockwise, that's a plus moment. This one gives us also clockwise, that's a minus. Okay, so we just write them like that. So it would be minus 200 times 500. I am writing these as millimeters, but obviously you can ditch these 2 zeros and think of them as, or let's say you can ditch 3 zeros and think of them as meters. So that would be the first one. Then you have the moment from FB. That would be then 500 plus 500. That's 1,000. That's 1 meter. So that would be 1,000, or that would be, let's say, FB times 1,000. And then eventually you have 300 times 1,500 is 0. Okay, so these are 2 equations, 2 unknowns. And from these, you can calculate FA and FB. FA will be minus 50 Newton, indicating that our direction was wrong, and FB is 550 Newton. Okay, so that's that. So basically what we have here would be a force of, this would be FA, a force of 50 downwards, and what we have here is a force of 550 upwards, okay? Assuming that these don't exist anymore because we just replaced them. All right, so this is the picture now that you have, and for this picture you want to draw, or you want to calculate your moment distribution. Okay, so I'm going to draw that picture. Let's say this is our beam. You have 300 downwards, that's the force, then 550 upwards, again 200 downwards, and 50 downwards, which kind of makes sense if you just look at it. 50 plus 200 plus 300, that's 50, that's 550 downwards, right? So if you want to calculate the moment here, you basically need to cut this structure there. So if you cut it there, what do you see? You would have a force 50 here. You would have your shear force downwards, and this is your moment, right? So if you write your equilibrium, you would see m plus 50 times x, you know, this distance would be x, is 0. So your moment would be minus 50x, right? Okay, so you can do that, and then you can also repeat this game. For instance, you can cut it further down. So let's say, sorry, somewhere here. Now, if you cut it somewhere here, you would have a 50 there, and you would have a 200 here. So your moment then, and then again, this is your V, this is moment. Your moment would have both contributions. So it would be m plus, let's say this distance would be x. So again, 50 times x plus that 200 times x minus, you know, 0.5. So this is 0.5. So that's 200 times x minus 0.5 is 0. So you can calculate m also here. Okay, so basically you would need 3 different functions for m, here, here, and here, to calculate that. And if you do that, everything is gonna work. It's perfectly fine. You can solve this problem. But this takes a little long. What we want to do instead is to use our Macaulay brackets, or discontinuity function. Okay? So if you use your discontinuity function, the solution for this problem simplifies significantly. See, your moment is minus 50 times x minus 0, okay, because, you know, this 50 is only at point x0. Then after that, you would have a very similar structure. It's minus 200 times x minus 0.5. Okay, so basically it tells you if you are here, only this one counts. But if you are here, both of them count. And then obviously you need to add that additional part, but that comes with a plus because 550 is upwards. And that would be x minus 1. All right, so this is your moment as a discontinuity function in one piece. You don't have to have these little pieces. And of course, this is very nice because now all you can, or all you have to do is to replace that in this equation and get your differential equation to solve. Okay, so you would say then, all right, EI V double prime is M, and that is your M. Okay, so that is minus 50 x minus 0 minus 200 x minus 0.5 plus 550 x minus 1.0. So you integrate once, that would be EI V double prime is so these powers are basically ones, right? So when you integrate them, this gives you that power 2 divided by 2. Or let's say the first one is basically minus 50x. That gives you minus 25x squared. Okay? So you get minus 25 x squared. Okay, it's x minus 0, so I'm just writing it as x. Minus 100 x minus 0.5 times, well, to the power 2, plus 500 divided by 2 is 275 times x minus 1 to the power 2. So that's the second one, and then you integrate it once more. And by the way, when you integrate it, obviously you have a constant here, I forgot. So you integrate once more. So you get minus 25 divided by 3, x to the power 3, minus 100 divided by 3, x minus 0.5 divided by to the power 3, plus 275 divided by 3 times x minus 1.0 to the power 3, plus C1x plus C2. Okay, now that you have this, all you need to do is to compute the boundary conditions. Or to insert the boundary conditions to compute C1 and C2. So what are the boundary conditions? If you look at the picture, you see that displacement is 0 here, the deflection is 0, here and here. So at x equals 0, deflection is 0. At x equals 1, also deflection is 0. You insert those two boundary conditions. So V at x equals 0 is 0. V at x equals 1 is also 0. From the first boundary condition, you immediately see C2 is 0. Because if you insert x0, all of these terms will disappear, and then this would be 0. From the second boundary condition, you find out that C1 is 12.5. Okay? So you are done, basically. At this point, you are done. If you want, you can also write this equation again using the boundary conditions. So you can say, well, your deflection function is 1 over EI multiplied by, what you have there. But you don't really have to do that. That's fine at this point. Okay, so this is the way you compute your deflection functions. All right, do you have any questions? There is one little thing I didn't talk about, by the way. If you think about the dimensions of these variables, E is Pascal, right? So let's say in our notation, that would be Newton per meter squared. I is meter to the power 4. Okay, so what you get here is, what you get here in this coefficient is something which is, inverse of that, obviously, is basically 1 over Newton meter squared, right? So you need to pay attention that, this coefficient that you want here, it would be basically in Newton meter cubed, so that your deflection would be meter, something like that. Okay, so it doesn't matter, but if you want to think of the dimension of C, for instance, because it's a constant, that constant has a dimension of Newton meter cubed, basically. All right, so that's that. The second exercise is here. So you are given this loading, and then again, as you can see, the question is, well, determine the deflection. It asks you to determine the maximum deflection, but the idea is not very difficult or very different from what we have done before. If you want the maximum deflection, you need to calculate deflection function and set its derivative to 0. Okay, so it's not far from that. And then again, in order to calculate deflection or deflection derivative for that matter, you need to calculate moment distribution and then use again the same formula that we just used before. So we need to do that. Now, there are many different ways of doing this. You can basically start cutting it like you usually do here and compute your moment. So you can compute your moment at the distance x here and another function at the distance x, and then basically, you would have like a jump function between the first part and the second part. You can solve that, that's perfectly fine. But what I want to do is to solve it again using the discontinuity function or Macaulay brackets, because I think that's the part that most of you are struggling with and it's new. So let's do that. Okay. To start with, we again start from our equilibrium. So we take this as free body diagram, and we assume that there is a moment here at A, and also there is a force at A. So we want to replace the support, and we need to calculate these reactions. Okay, so this is a fairly simple problem. Again, if you think of the area of this triangle, you can then replace this triangle with a single force with that area. So if you do that, the area of the triangle is 1.5 times 30 divided by 2. So that is that's 45 divided by 2, 22.5. And the distance is, well, 0.5 from here and 1 from left. Okay, so we know that. Also, if you think of the slope of the line, we don't need it now, but we will need it soon. If you think of the slope of the line, you can also calculate the slope of that line. That's 20. Okay, so right? So it is 30 in 1.5 meter. That would be basically 20 in 1 meter. So that's the slope of the line. So if you wanted to write this equation of the line as, I don't know, y equals mx plus b, you can do, and b would be 0 anyway here. Okay, so back to our equations, we write our equilibrium of forces. So you would say equilibrium of forces in y direction is 0, assuming upwards is plus, and equilibrium of moments, let's say with respect to A, is 0, again assuming counterclockwise is positive. And if you do that, they are very simple, obviously, for this example. Then FA would become 37.5 kilonewton. You can immediately see it, right? I mean, you have a force here, you have a force here, that's it. And so this would be 22.5 plus 15, that's 37.5. And then you can also calculate the moment at A, which, it would be basically equal to that 22.5 times its distance, which is 1, plus the moment of 15 times its distance, that is 3. So MA would be 67.5 kilonewton. Okay. By the way, usually we write it as equilibrium, so they are coming on the left-hand side with a minus, and it is 0. I jumped through that. Okay, so that is MA, that's FA. Now, instead of having this picture, what I want to do is to basically assume that, okay, we have a distributed load that comes all the way to the end. Okay, so assume we have this. And then subtract this from it. Okay, so this is the way I want to approach this problem. And then if you do this, your problem basically splits into three very nice problems, or three zones. And for each of these zones, we know exactly how to use our discontinuity functions very nicely. Okay, they become very, very standard. That's exactly what I want to do here. Okay, so let me just draw it. That's that. Okay, so this is our first problem on top, and then somewhere here, I would have this distribution, and this distribution is a constant, right? And then I would have this one with the same slope. But the idea is that all of these must be equal to all of this, okay? And how much is this? Remember, we had the slope of the line to be 20. Now, if you multiply 20 by 3, you get 60, right? So this is 60, and this should be altogether 60, okay? Just so that we know. And then again, this is 60 downwards, by the way. You know, when you write this slope, okay, I called it 20 because mathematically it's 20, but remember, when we want to calculate, you know, the distributed load, it's basically this, right? The distributed load is minus, so it's kind of minus 20. Okay, so that's that. All right, so now that you have these three functions, I would like to write our moment for each of them. And then if we write the moment for each of them, we can use our equation. So we want to use the equation EIV double prime equals M. But we just don't know how to get M yet. Now, remember, M prime is V, right? And also remember, V prime is the distributed load itself, okay? So here we need M, and M would be actually complicated to calculate for this picture. But what is not very complicated to calculate is the distributed load. We can, I mean, you actually see what the distributed load is. It's linear, constant linear. So we calculate this, we integrate it to get V, we integrate it to get M. Okay, so that's the trick. We want to go backwards, then we integrate. So what you need to do is to write your W for this picture. Okay, so for this picture, we have these three parts. What is your W here? It's the slope of the line times x minus 0, because x starts from 0, to the power 1, right? It's a linear function. And that M, by the way, is minus 20. Okay, so that's 20 downwards. Okay, so that's not too bad. For the second part, what is W? It's just constant. Okay, so if you think of this value as W0, that would be W0 times x minus a to the power 0. And then again, x sorry, A here is 1.5 because it starts from this coordinate, it starts from 1.5. W0 is this value, and pay attention, it's the way I draw it, it's at the bottom, but it's pointing upwards, right? So it's actually a plus value, okay? And that constant that we are talking about is essentially the same as what you have here, right? It's 30. Okay, so we want to start from 0 here, right? So because this is 30 downwards, you need to start from 30 upwards so that you basically get this picture. Okay, so this would be then plus 30. Now, eventually for the last part, here W is very similar to the first part, is also M times X minus A to the power 1 though, okay? And then again, A here is 1.5, and M here is now plus 20. Does that make sense? Okay, so this is really the most important step of this. Now, if you understood this part, the rest is very easy. Then you just say, okay, my W is the sum of these three parts. And because you are using this discontinuity function, you can, nicely just add them up without being too worried. So the first one is minus 20 times x minus 0 to the power 1. Okay, so that's that. Then we just add this to it. Plus 30 times x minus 1.5 to the power 0 plus 20 times x minus 1.5 to the power 1. So this is your W, and now all you have to do is to integrate it to get V. Then you integrate it again to get M, and only then you still need to integrate it twice to get the deflection. Okay, so you need to do a lot of integrations, but I think the way that it goes forward from this point on, it's nice. So that's your W, then you integrate it, you get V. So integral of this is minus 10, x minus 0 to the power 2. Obviously, you don't have to write 0, but I just want to emphasize. Then here, okay, this is 0, so it just becomes 1. So it would be plus 30 x minus 1.5 to the power 1 now. Then plus 10 x minus 1.5 to the power 2. But then you also need to add a constant here, right? So there is a constant adding to this. And now that constant would be your shear force at x equals 0, right? So again, you can say it is a constant. And then your boundary condition would be that your shear force, let's say at x equals 0, is, I don't know, Fa, right? And then at x equals 0, these will all be 0, so this basically becomes your Fa, And also it comes together with your Macaulay bracket, right? So this would be then Fa times x minus 0 to the power 0. Does that make sense? Okay, so that is your shear force. Then you integrate it again. Now you would have minus 10 over 3 x minus 0 to the power 3 plus 15 x minus 1.5 squared plus 5. Sorry, plus 10 over 3. X minus 1.5 to the power 3 plus Fa And what was FA? Was 37.5 anyway. So 37.5 times x minus 0 to the power 1 for now, okay? All right, and then we add a constant again. Let's say this constant is C2. And then again, we play the same game. What if x is 0? M at x0, we know it, right? We calculated M, right? At x0, all of these, they disappear. So this would be your M at x0. And by the way, if you remember, because of our convention, and this is the internal M, you get a minus here, okay? So this would be basically minus MA times x minus 0 to the power 0. Okay, and then again, MA in this picture or in this computation is just 67.5, as we just, here we have calculated it. Does that make sense? Okay, so this is your M, and then what you need to do at this point is to use this into our formula EIV double prime. And as I said, all you have to do is to integrate these 2 more times. I'm not going to do that. As you can see, it gets just longer and longer. But you get the idea. Now, integrating from this point on, it's very easy. And then if you integrate more, you still get 2 more constants or unknowns. Again, let's call them maybe C3 and C4. But then you need 2 boundary conditions in terms of deflection or the derivative of deflection to get those. And if you look at the picture, those boundary conditions, first of all, deflection is 0 here, right? So that would be 1. And also the derivative of deflection is 0 because it's clamped. Okay? So those 2 boundary conditions are V at x0 is 0 and V prime at x equals 0 is 0. Okay, so if you do all of that, you would have your V as a function of x. Once you have your V as a function of x, you can set its derivative to 0 to see where it is minimum or maximum, right? So that's what the question wants. The question asks you here to determine the maximum deflection. So once you have V, you can also, let's say, set V prime to 0 and find out what is Vmax and where it is happening. So Vmax is basically minus 12.9 millimeters. It's minus because it's downwards, and it's happening at x equals 3. Okay? So this is the way to solve this problem. And then again, because we use this Macaulay bracket, I think it was a little non-standard. But if you split it into multiple parts, it gets a little more complicated than this. Okay, but that's it. Do you have any question? All right, so this was the second exercise for this recitation. All right, the next one asks you to determine the value of A so that the displacement at C is equal to 0. Okay? So, you have different ways of solving this. Again, you can also start just solving it as it is, but I find it particularly interesting also for learning purposes or for teaching purposes that we use our method of superposition for this. So if you use method of superposition, you can take this first, solve the system, and it's a very simple system because it has only one external force, and then we take this, and then we solve the system. For each of those, we calculate the deflection at point C, and then we set that to 0. the summation of those calculations. So what I'm trying to say is the following. Let's use principle of superposition. What you want to do is to think of this as two separate systems. Let's say this is your first system. Both of them, obviously, they have the supports. So you have a support here, and you have your support here. Okay, this one is a roller. So both of them have these. So I'm going to just duplicate this. So you got these two systems. Now, system 1 has only a P that is applied here, and system 2 has only a P that is applied here. Okay? Now, for each of these systems, you can calculate the deflection at point C, and then you add them up and you set them to 0. So you want V at point C from system 1 plus V at point C from the system 2 to be 0. Okay? And for each of them, you can use also this continuity function, Macaulay bracket, and so on. So I can try to solve it, but I think it is best if I leave it here for the sake of time. But just pay attention that, of course, if you have here P, it's in the center. So the reactions would be P over 2, P over 2. But if you, in the second system, the reactions would be P times A plus L divided by L from the left one. And then from the right one, you would have PA over L. Okay, so you just use Macaulay bracket for each of these, and then you add them together, you set them 0, and eventually, if you did everything correctly, you would see A should be L over 3. Okay. Again, the individual calculations are not very complicated. We don't have distributed load or anything. It's a fairly simple problem, but it just gets long a little. All right, so this was the next exercise. The last one is this. We have done a more complicated one in the lecture when we had let's say, a distributed loading. So this is not a particularly complicated problem either, but it's a nice exercise for you. You are asked to calculate, again, the shear and moment diagram, and in order to do that, obviously you need to compute the reactions, the moment reactions at the supports, and also the force reactions. And then again, the system that you have here is a statically indeterminate system. So in order to do it, you need to use some sort of, let's say, compatibility or superposition. So if you do that, and then again, I'm not going to write all the details, but the idea would be that you have here, let's say, AY and BY. Okay, and then you would write also your moment equations. And if you calculate this, well, I mean, if you go through the steps, for AI you get WL over 2. For the moment at A, you get WL squared divided by 12. And if you draw your shear and moment diagrams, okay, your shear diagram looks like this. This is one of those examples that having or starting from the graphical approach, it pays off really highly, because, if you think of the moment and so on, maybe it's complicated. Again, it's statically indeterminate. You need to be careful. But if you look at the shear force diagram, it's so simple. You know, this is your x coordinate. The entire force that you have is WL, right? And then you have a symmetric system. So you can immediately see that you have WL/2 on each side, right? So this would be WL/2. This would be minus WL/2. Okay, and if you basically think of the integral of this, you get your moment equation, right? So, and you know the moment is maximum at the center too. So you can also immediately draw your moments. Okay, let's say it would look like this. And then, as I said, the moment must be 0 in the center, and then it should be symmetric and non-zero on the sides. I don't know, it's going to look like this. Okay, so this would be your moment diagram. This would be WL squared divided by 24. And then on each of these sides, you have minus WL squared divided by 12. All right? So that's it. Again, you can approach this problem graphically or by calculations, but I think you will find out that you can do it using the knowledge you have learned. I just emphasize this is a statically indeterminate system, so although you want only V and M, you still need to go through your deflection to get your compatibility constraint or compatibility equation to be able to solve this. All right, so that was the last exercise for today.